Next section is dimensionless analysis of the pipe flow. Most of the turbulent pipe flow analysis are based on the experimental data and semi-empirical formula. These data are expressed in the dimensionless form. The overall head loss for the pipe system consists of the head loss due to the viscous effects in a straight pipe in terms of a major loss. Okay, we use the symbol HL major, and the head loss in the various pipe components in terms of minor loss or HL minor. Normally, it comes from the change of the flow geometry. Okay. So the combination of the total loss is equal to the combination of the major loss plus the minor loss. And the next is the major loss, the pressure drop, and head loss in the pipes are dependent on the wall shear stress. Okay, between the fluid and the pipe surface. The difference between the laminar flow and turbulent flow is the shear stress of the turbulent flow is a function of density of the fluid, but for laminar flow, the shear stress is a function of the viscosity only. The pressure drop for the turbulent flow in the pipe can be written in the functional form. See, the pressure drop is a function of velocity, diameter, length, roughness, and viscosity and density. So there we have on many parameters. This figure shows that for turbulent flow there is a relative thin viscous sublayer formed in the fluid in the pipe wall, and this is the viscous sublayer del S or Y divided by this less than 1, and this is the sublayer thickness. So in this case there are 7 variables. For K7 we have 3 reference dimension is 3, so we can written the dimensions form about 4 form in this equation. Okay, we have 4 dimensions variable, and for this one is for the roughness. Okay, roughness, and this is for the sublayer thickness, viscous sublayer thickness. Okay, it's bigger than the relative roughness. Okay, and for L over D is dependent is a factor also we put in front of the relationship, and we replace the delta PD divided by in terms of the friction factor. So in this we put in terms of friction factor, and you can write that equation of delta P is equal to the friction factor times L over 2D rho V square over 2G, and in this case the friction factor is a function of the Reynolds number and the roughness divided by D. The epsilon E is the thickness of roughness thickness. Okay. And for laminar flow, F is a function of the Reynolds number 64 divided by the Reynolds number, and it depends on it's independent of the roughness. Okay, for the turbulent flow, the friction factor is a function of both Reynolds number and the relative roughness. Okay, so in this case we can write that is the roughness and we divided the roughness divided by the diameter. So we call it relative roughness. And from energy equation, we write equation between 2 points, and with the assumption of the constant diameter, d1 equal to d2 and v1 equal to v2, and horizontal pi, pi with the fully developed flow, alpha is equal to so the delta P become the different pressure and equal to gamma HL. So we can write equation for head loss is equal to FL over D V square over 2G. We call the Darcy-Weiss this equation that for the called Darcy-Weisbach equation is valid for the and a full developed steady incompressible pipe flow. And for the friction factor F is determined from the Reynolds number and the relative roughness. Okay, this is the number and relative roughness. Typical roughness value for various pipe surface given in the table. That is for the equivalent roughness epsilon E for different type of the pipe. If the smooth, for example, as a plastic or glass is very smooth, the roughness is close to zero. And drawn tipping is the copper pipe, very small. And figure 14.2 show the functional depending on the F on the number and roughness that we call the Moody chart. Okay, that is the Moody chart. Okay. After we on the relative roughness, E over D is considered larger than the given. Normally is for the new pi is large, and not only change this value can be changed once the effective diameter when it's used in longer time. Okay. And the next for the laminar flow based on the Moody chart, Moody diagram. Okay, laminar flow is the F is the 64 divided by Reynolds number. This range for the laminar flow. Okay, and for turbulent flow, friction factor is a function of both for the turbulent flow. In the case of the turbulent flow, that is, the friction factor is a function of the roughness. It is dependent of the Reynolds number that we call the complete turbulent flow. That is this part is complete turbulent flow. The friction factor is a function of roughness only, and between this part, laminar flow and complete turbulent flow, the friction factor is a function of both of the roughness and Reynolds number. Okay, for flow with the moderate value of Reynolds number, the friction factor is indeed dependent on the both Reynolds number and relative roughness. Okay. And in this case, if laminar is between 2000 and 4000, its transition may be laminar or turbulent. Okay. For smooth pipe, the epsilon is go to zero. F is not zero. That is, there is a head loss in the any pipe, no matter how smooth the surface is made, result of the no-slip boundary condition that required any fluid to stick to any solid surface if the flow is over. So, and this shows the Moody chart for the entire non-laminar range in terms of equation in Moody chart. Okay, so this the friction factor is a function of roughness and no number in terms of the equation.